Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss Weiss's theory of ferromagnetism and ferromagnetic domains. Let's begin. Weiss's theory of ferromagnetism based upon two hypotheses. The first one is the atomic magnets of a ferromagnetic substance are grouped into a number of certain regions, and these regions are known as domains which are spontaneously magnetized. Let me understand it. When we relate in between paramagnetic substances and ferromagnetic substances, in these two conditions, the atoms present in their outermost shell, the number of electrons have odd number of electrons. Therefore, they attain a permanent magnetic moments. Without the application of external magnetic field, the net magnetic dipole moment is not zero. Therefore, a permanent magnetic moment exists in case of paramagnetic substances as well as ferromagnetic substances. But what is the basic difference between para and ferromagnetic substances? Let me differentiate it. In case of ferromagnetic substances, the magnetic moments of individual atoms are coupled to that of neighboring magnetic moments very strongly due to the exchange of interactions. In that of figure, we can easily understood is a paramagnetic substance. Paramagnetic substance. Inside that of paramagnetic substance, it has permanent magnetic moment and the atomic dipoles are randomly movement like this. But in case of ferromagnetic substance, that is without the application of magnetic field, B naught is equal to 0. B naught is equal to 0 without magnetic field. B naught, B vector is equal to 0. In case of ferromagnetic substance, as we say, these magnetic moments of individual atoms are coupled to what? Coupled to the neighboring magnetic moments very strongly through exchange interactions, and these large number of magnetic dipoles get aligned in the same direction. From large number of small effective regions and these small effective regions are nothing but domains. In that section, the alignments like this. In this section, the alignments like this. In that section, maybe the alignment all are in the same situations, same directions, they are aligned. And these regions are known as the domains. There are a large number of domains present inside that of ferromagnetic substances, and these domains are supposed to exist throughout that magnetic materials, and there will be a huge number of such domains present inside that ferromagnetic substances. And these domains, inside that of domains, there will be the magnetic moments, and each domain is magnetized to the degree of saturation in one direction. There will be one direction, this is one direction, that also in another direction. Therefore, the normal state of that of ferromagnetic substance, when that external magnetic field is absent, the different domains are randomly distributed. Hence, their magnetic moment is 0. Without the application of external magnetic field, if B is equal to 0, then the net magnetic dipole moment also mu B will be 0 throughout that of entire ferromagnetic substance, and the net magnetic dipole moment is decided by individual domains. Next, if we apply an external magnetic field, therefore, the magnetic moment of that of substance increases. When we apply the external magnetic field, therefore, all the domains, the magnetic dipole moment are aligned in the direction of external magnetic field. With applying external magnetic field. Means B not equal to 0, and these domains gradually increases, there will be different kinds of methods, like by the displacement of boundaries or the rotation of domains are the two way in order to increase the size of the domains inside that of ferromagnetic substance. That is the first hypothesis proposed by Weiss regarding ferromagnetism. Next hypothesis, with each domain the spontaneous magnetization is due to the existence of a molecular field which tends to produce a parallel alignment of the atomic dipoles. Look at that situation, which are spontaneously magnetized inside that of domain, these are spontaneously magnetized, but why? Which cause is responsible for their spontaneous magnetization? That will be the cause why inside these domains they are spontaneously magnetized, due to the existence of a molecular field, and that molecular field tends to produce a parallel alignment of the atomic dipoles. These atomic dipoles within that of domain are parallelly aligned due to that molecular field. So, what happened at that of situation? At that of situation, the internal field is equivalent to magnetic field. Let that magnetic field be Sm, and that Sm proportional to the intensity of magnetization. I within that of particular domain, within a domain, that is that Sm is directly proportional to the intensity of magnetization. Here we can use a proportionality constant, that is lambda, the proportionality constant lambda and the Weiss constant, which is independent of temperature, that is independent of temperature. Equation number 1. If the external magnetic field is applied, if we apply the external magnetic field H, then the effective magnetic field on atomic dipole is equal to H effective will be the external magnetic field H plus the internal magnetic field that is Hm is equal to lambda I plus lambda I. Equation number 2. We know from Langevins theory of paramagnetism, here we using Langevin theory of paramagnetism. We have intensity of magnetization I is equal to N mu m L of x. Let equation number 3, where N, that is number of dipoles per unit volume, and mu m, that is individual magnetic moment. L of x, that is Langevin's function. For saturation magnetization, the product of N into mu m is equal to Is. Here N into mu m is saturation magnetization, that is represented by Is, which corresponds to saturation. When all the magnetic moments, that is all the moments are aligned along the applied magnetic field. Then intensity of magnetization is Schwarzschild, applied magnetic field direction, that is I of S is equal to N into mu m. So, putting that value, we have putting this value, we have I is equal to I of S L of x. Equation number 4, where L of x is equal to cot Hx minus 1 by x. We have already discussed it, that is Langevins function. Now, therefore, I divided by Is is equal to L of x, that is equal to Langevin function cot Hx minus 1 by x. As equation number 5, where x is equal to mu mb divided by kt. You can refer to know about this as Langevins theory in paramagnetism. therefore x is equal to mu m in place of b, that is mu naught into h effective, b is equal to mu naught into h divided by kt, or x is equal to mu m mu naught in place of h effective, that is h plus lambda I, h plus lambda I divided by kt. Equation number 6. But in case of ferromagnetism, for ferromagnetism, as we say, there will be the process of spontaneous magnetization. For ferromagnetism, spontaneous magnetization takes place. Even when H will be 0, H will be 0, but spontaneous magnetization takes place in case of ferromagnetism. Therefore, H put it as 0, x is equal to mu m mu 0 mu naught lambda I divided by kt. From this value of I, we can obtain x kt divided by mu m mu naught lambda. Now, we can obtain I divided by Is. For Is, let we introduce n into mu m. So, value of I as x kt divided by mu m mu naught lambda into value of Is as n to mu m, or I by Is is equal to x kt divided by mu naught lambda n mu m square. Equation number 7. Look that two way. Here I by Is is equal to L of x, Langevins function, and again I by Is is equal to that much. These two equations can be solved by taking the graph. Equation 5 and 7, equation 5 and 7 can be solved graphically. if we plot the graph in between I by Is in y direction and x along x direction, we obtain two graphs for these two equations. For equation number 7, the graph is looking like this. For equation number 6, the graph is looking like this. That is for equation number 7, that for equation number 6. And these two graphs are intersect at origin as well as another point, let B. Two points let we choose from that of line, one is A, another one is C. These two curves meet at O and B. The solution of I by Is is 0. If we take in that point, that is not true. Therefore, I by Is is equal to that point, which one is equal to BD. Now, the slope of the straight line curve 7 is given by, now the slope of the straight line curve 7 is given by the slope of the line curve, slope of the line curve is equal to kt divided by mu naught lambda n mu m square. Here x is equal to 1 is put it. Using that equation number 7, we say the slope will be that much. For x tends to 0, then the Langevin function L of x is equal to x by 3. So, the slope of the straight line, slope of the straight line is equal to 1 by 3. Therefore, slope of the straight line curve becomes slope of the straight line curve becomes, we equate these two equations as kt divided by mu naught lambda n mu m square is equal to 1 by 3. From that equation the value of t can be calculated, that will be mu naught lambda n mu m square divided by 3k. The temperature is nothing but Curie's temperature. So, Tc mu naught lambda n mu m square divided by 3k. Equation number 8, where Tc is the Curie's temperature. An important point you can write here, the state of magnetization, is possible even without applied field, without applied external magnetic field. For temperature below the Curie's temperature, below Curie temperature and above Curie temperature, the ferromagnetic materials, becomes paramagnetic one, becomes paramagnetic materials. We have already discussed that point. As above Curie's temperature, the ferromagnetic material becomes paramagnetic materials in the topic related to Curie's law. The state of magnetization is possible even without applied magnetic field for the temperature below Curie's temperature, and above the Curie's temperature the ferromagnetic materials becomes paramagnetic one. So, here with the help of this video lecture we understand the concept of Weiss's theory of ferromagnetism and idea of ferromagnetic domains. That Weiss's theory based upon two hypotheses, one hypothesis on domains, another one the idea of spontaneously magnetization. Then mathematically we show I by Is, again I by Is. These two equations are solved graphically by plotting the graph. From these two equations we obtain Curie's temperature and our observations based upon that Curie's temperature. So, with this useful and informative notes, let me wind up this session. Thank you.